Okay, so this is part C of separations homework 2, and we'll be implementing code for calculating the bubble pressure, dew pressure, bubble temperature, and dew temperature calculations for an isopropanol water system using the NRTL activity coefficient model, same one that we used in part B. And we're going to be generating a constant temperature binary VLE of isopropanol and water at 350 Kelvin. And then we're going to generate the constant pressure binary VLE at 1 bar and compare with plots from online. So to start, I've already got our library put in, and I've already have the code to access the data for isopropanol and water. And since we're only using two components, the ratio would be 30% to 70%, 30% isopropanol, 70% water. So to start, we want to start with defining our NRTL for bubble pressure. So we're going to have T, and then we're going to define our partial pressure of Y. So this is X times P dot NRTL of gamma times of X on T, and then we're going to multiply this by our vapor pressure at temperature T, and then define our pressure, which is going to be NP dot sum of our partial pressure of Y, and then we're going to simply return with pressure and partial pressure divided by pressure. Okay, so now that we have our bubble pressure defined, we're going to do kind of the same thing for the dew pressure. And since this is in consideration of vapor, we're going to use Y instead of X. And we're going to have our T and niter, which equals 100. And then our tolerance, which is 1 times e to the -6th. And now here we're going to define our vapor pressure, which is just P dot PVAP of T. And then we want to define our gas phase composition, which is divided by NP dot sum, or no, sorry, this is NP dot ones underscore like of Y. And we're going to have our X, we're going to have our old pressure as our 1 divided by NP dot sum of Y divided by G times PVAP, and have our X, which is Y times our old pressure divided by G times PVAP. And then we're going to have our X defined as divided by NP dot sum of X. Okay, I actually messed a little bit. Crucial step. So for I in range of niter, then it will go to our P old, etc. And then our G will equal P dot and our TL underscore gamma of X and T. And then we'll have our new pressure, which is the exact same, which is right there. And then we're going to state that if this is almost right, if np.abs of p new minus p old, and this is going to be divided by p new, is less than tolerance, then it's going to break the loop. And then we want to not only know x and p new, we also want to know I. Now we're going to go ahead and define our constant temperature we've been given, which is 350 Kelvin. And then we're going to state our liquid compositions, which is np dot, or no, sorry, np dot line space of 0, 1, and 101. And then we'll have our vapor compositions, which we're going to make into matrices. Same with our bubble pressures, which are also terms of matrices. Okay, so now we're going to find for x1 within our x1s. It's supposed to be in. We're going to set our p and our y1 underscore, which equals, and our TL underscore, our bubble pressure, we're going to make in terms of array of x1 and 1 minus x1 in terms of temperature as well. And then we're going to take our bubble pressures dot append in terms of T, and then our y1s dot append in terms of y1, and then we're going to set our bubble pressures equal to np dot array of bubble pressures, and our y1s, which we're going to do the same thing as set np dot array, but in terms of y1s. Okay, so now we got our bulk of the code done, so now we just have to make our chart to show what we made. So fig equals make underscore subplots. Then we will have our fig dot add underscore scatter, where our x is equal to our x1s, and then our y is our bubble pressures, and then the name we'll give for this is bubble. Then we'll describe our do, which is x equals our y1s y is also bubble pressures, and the name will be do. I'm just going to add a little bit of I just want to get this a little bit better to fit on the screen, and that should be good. Oh, right. Looking over the code, and it's supposed to be pressure, not temperature. There we go. That is all good. So as you can see, we have our bubble pressure going a little bit up and then starting to kind of smoothing out there, and our dew pressure increasing and then coming back down, and we reach this azeotropic class, which basically shows that it's coming at a little bit of an equilibrium, and our vapor and liquid compositions are at pretty much the same level at this point. And from there, they kind of break off, but they're pretty close to being at equilibrium. And so that concludes this part of the section, and the next part we're going to be getting into part 3. So now we're going to start with part 3, which in this case is going to be generating our constant pressure binary VLE at a certain pressure, and then we're going to compare it with online charts. So first we're going to go ahead and define our bubble temperature, which in our TL underscore bubble T terms of X and pressure. Yep. And then we go ahead and define our initial temperature, which is NP dot sum of X times our P dot NRTL NP dot sum is supposed to be P dot TB pressure, and then we're going to go ahead and define our fruit as we've done previously to find our roots to use, and then we're just going to go ahead and return with NP dot sum of X times P dot NRTL underscore gamma of X and T times our P dot PVAP. No, it's not correct, but P, all that minus 1. And then we're going to go ahead and define our temperature, which this one is going to be our SP dot optimize dot root underscore scalar, where we're going to use our fruit, our X naught, which equals our T naught, and then our method will be our secant, and then just dot root. And then we're just going to go ahead and return with T, and then we're just going to go ahead and copy and paste to save time because it's just this. And yep, there we go, and this should be correct. Yep. Okay, so now we're going to try and define our dew temperature, but first we're going to define our dew pressure in terms of Y and T, and then we're just gonna go ahead and say our PVAP is P dot PVAP. We're gonna return with P and Y times PVAP, and now we can define our dew temperature, which is in terms of Y and P, and we're just going to define our T naught, which is the same thing as bubble temperature, but in terms of Y instead of X. And we want to use our define fruit again, where we're going to return with np.sum of sorry, it's not np.sum, it is our due pressure in terms of y and t, but we're taking that initial value and subtracting it by our pressure. And then we're going to do the same thing with t equals our SP optimize the same exact equation, and then we're going to return with t and y times p divided by p dot pvat of t. Okay, so now what we're going to do is we're going to define our p, which is to the fifth, since we did have to be specified that it's 1 bar, but this is going to be in pascals. And then we're essentially basically just copying this entire code. However, we are going to change a few things, and because we're not looking at bubble pressures, we're looking at bubble temperatures. So P's are T's and T's are P's. It's going to be T, then we're looking at T, T, so also in terms of temperature, and therefore that is also in terms of temperature, and then we're just going to see if that works. Okay, yep. And then we're going to go ahead and make our subplot to display this information. However, we do have rows and columns, which is 2. Yep. And then fig.add underscore scatter, which Gemini got it correct. And then we're going to do the same thing for do. It's going to be 2. And then we're going to add another line of code, which states that x is x1s, y is y1s, and then we're just going to add our row, which equals 1, column, which equals 2, then fig dot scatter. This time we're going to make x in terms of 0, 1. Same thing with y, where we're going to say that. However, add a few more things, which is lines show legend is equal to false, and then we're going to change the line color to yellow to just make it a little bit more definitive. I think we have to also put a show legend as false here as well. Make that 600. Then I think that should be good. Okay, so it turns out I accidentally had this as column 2, so we wanted the dew pressure or the dew curve and the bubble curve to be on the same graph, and with it being column 2, it was shown here. So now that we have our two graphs, we can see that on our binary VLE, our bubble and dew pressure as temperature is decreasing, it starts to converge and um, start becoming more aligned with each other. And we can see that, suppose if we take 359 degrees on our bubble, has a vapor composition of 0.05, whereas the same one will have 0.407 on the bubble, or the dew. And you can see our azeotrope form right here during our reaction. And this is very similar to our the online versions. This is the VLE diagram of water and isopropanol. It's at 1.013 bar, which is pretty much practically the same. So it looks very identical to our plot that we've made here. And then if we search up isopropanol in water azeotrope, we can see that although, okay, it's 2-propanol, okay, isopropanol in water, kind of hard to see, but we can see our azeotrope graph pretty much identical to the one that we see right here. So we've successfully created a accurate representation of our constant pressure binary VLE and constant temperature binary VLE, and we've been able to prove that it looks identical to the one posted online as well.